Hello to my lovely AP Chem dual credit kids. Today we're going to talk about sections 4 through 6 on the gas laws chapter. Last video we covered sections 1 through 3 on the individual ways to convert pressure units and how to interpret Boyle's, Charles, and Avogadro's laws of gases. Today we're going to put those three laws together and we're going to create the ideal gas equation. So if we put all of them together, we get some kind of a relation that looks like the one you see on the screen. Now, one thing you should be noticing is that these three interpretations of Boyle's, Charles, and Avogadro have left out that little proportionality constant K. In fact, they do this so that when we move on, we can see that we actually have to create our own proportionality constant in the ideal gas law. Now, the one that we will most commonly use is this one at the top. Sometimes we may use 8.314. It really depends on the units. And you're going to notice that this table actually describes how different units of pressures and different units of temperature and different units of volume can come into play. For us, we're going to focus on this first one. Again, it's the most common, it's the most useful. It's a number that we will use multiple times and not just for gases, but it is introduced here. The ideal gas law, which is one you've all seen before, states that pressure and volume are going to be related to temperature in moles with the proportionality constant as well. So as pressure goes up, temperature should also be increasing. As the number of moles increases, the volume that it takes up should also be increasing. The ideal gas law takes into account Charles, Boyle, and Avogadro and obeys all three of those relationships. From there, we can talk about how we can get more than just this type of information from the ideal gas law. In other words, yeah, it's nice to know pressure, volume, moles, and temperature, but sometimes we want to get different pieces of information. For instance, maybe we want to know the density of the gas we're working with. And so we can manipulate the ideal gas law by dividing both sides of it by V and by RT to get moles over volume on one side. And then when we don't want to go from moles to mass, we just have to multiply by the molar mass. So when we multiply moles times molar mass, we are left with mass, and that puts M over V on one side. You should recognize this as mass over volume is density, and this capital M becomes molar mass moving forward in our formulas. So now we have a way to manipulate the ideal gas law to identify different pieces of information about different gases that we may be investigating. And in fact, understanding how to get density from these things is really useful if we only have some small pieces of information instead of having a lot of different pieces of information about our specific ideal gas situation. Now, that being said, we can also use this equation to find molar mass. And remember that density can always be substituted out for mass over volume. So if we wanted to, this equation could also then be, if we wanted to, this equation could then become mass over V times P times R times T. So we can get the molar mass of something using this particular formula, which is one you should recognize because we did this in the dust-off lab. Okay. From there, we can talk about our next big topic and the last one in this video, which is Dalton's law of partial pressures. It basically states that if we have a mixture of gases, think the air you breathe, that the total pressure of all of those gases added together is going to be equal to each of the individual gases' pressures added together. So for instance, if I'm talking about the mixture that is air, we would have pressure of air would be equal to the pressure of the O2 plus the pressure of the N2, plus the pressure of the maybe helium gas, plus the pressure of the argon gas, etc., etc., etc. Lots of different gases in our atmosphere. Okay, so but what we're saying is that if we add all of them together, we get the total pressure. From there, we can introduce the idea of a vapor pressure, which is one that we also kind of covered in the lab we did last week, where if you think about the gas directly above a liquid, that vapor, if you will, has its own pressure that needs to be accounted for when we're talking about a total gas amount. And so in our lab, we had to account for the total pressure being a combination of the butane plus the water that we were dealing with. Okay. All right, so that being said, if we wanted to find the vapor pressure of the water, a lot of times we talk about vapor pressure above water because water is the most common solvent. We're going to use a table. pH2O is something that we can usually get from a table, or we can calculate using Dalton's law of partial pressures. Okay, but it's not something we can ignore. A lot of times we do have to correct for that water vapor. All right, so that is all I'm going to talk about as far as lecture is concerned today. The next thing you're going to work on are some problems over partial pressures and ideal gas laws. A lot of it's going to be a review, but you need to get through the review so we can talk about kinetic molecular theory, which is the next big topic in this chapter. So for now, I want you to move over into your OneNote notebooks and start working on the practice problems over sections 4 through 6.